Welcome back to G Fun Facts Online. Today, we are diving deep into a story that is unfolding right now in the late months of 2025. It is a story about a war, a silent, invisible war that humanity has been losing for decades. But it is also a story about a turning point, a moment where silicon and biology have finally merged to give us a fighting chance. We are going to talk about the digital renaissance in medicine, specifically how artificial intelligence has taken over the hunt for antibiotics, achieving in just a few years what human chemists struggled to do for half a century. Let's set the scene. The year is 2025. For the last 40 years, the pipeline for truly novel antibiotics has been effectively dry. We talk about the golden age of discovery in the mid-20th century, the era that gave us penicillin and streptomycin. But that era has long since rusted. We have been staring down the barrel of a post-antibiotic era, a terrifying reality, where routine surgeries, C-sections, or even a simple scrape in the garden could become a death sentence due to infection. The adversary is ancient and evolving faster than we are: superbugs. Bacteria that have learned to survive our most potent medicines. But here, in late 2025, the narrative is changing. We aren't just finding new drugs. We are designing them from scratch using generative AI. This isn't science fiction anymore. It is the new reality. Today I want to walk you through exactly how this technology works, the specific molecules it has created, and why this marriage of technology and biology might just save hundreds of millions of lives. To really appreciate the magnitude of this AI revolution, we first need to understand why we stalled in the first place. Why did the discovery stop? For a long time, antibiotic discovery was a game of chance. It was known as the Waxman platform. The methodology was simple but labor-intensive. Scientists would go out into the world, into backyards, forests, even ocean beds, and scoop up soil samples. They would then screen the bacteria living in that dirt to see if they produced toxins that killed other bacteria. It makes sense, right? In the microscopic world, bacteria are constantly fighting each other for resources, so they naturally evolve chemical weapons. We just harvested those weapons. This method was incredibly successful in the 1940s and 50s. It gave us staples like vancomycin, tetracycline, and erythromycin. But by the 1980s, we hit a wall. We had picked all the low-hanging fruit. We kept analyzing soil samples and finding the same molecules over and over again. The search became too expensive and yielded too few results. Major pharmaceutical companies looked at the balance sheet and essentially abandoned the field. Meanwhile, the bacteria didn't stop. Through our overuse and misuse of existing drugs, pathogens like MRSA, Acinetobacter baumannii, and Neisseria gonorrhoeae developed thick armor. They evolved. We needed structurally new molecules, compounds that attack these bacteria in ways they had never seen before. But human intuition is limited. We tend to modify what we already know. We hit a creative wall. Enter the machine. The application of AI in this field has happened in two distinct phases. If we look back at the history of this technology, we can think of these phases as the Librarian and the Architect. Phase 1, the Librarian phase, occurred roughly between 2018 and 2020. This was the era of predictive AI. In this phase, scientists weren't asking the AI to create anything new. Instead, they used it to sift through massive existing libraries of chemicals. Imagine a library with millions of books, where each book is a chemical structure. Humans can't read them all. But you can train a deep learning model on a dataset of molecules, teaching it which chemical features are associated with killing bacteria. The AI then acts as a super-fast librarian, reading through these millions of molecular books to find hidden gems that humans missed. This approach led to a massive breakthrough in 2020 by researchers at MIT, the discovery of halicin. Halicin was a triumph. It was a molecule that was originally being investigated for diabetes. A human looking at it wouldn't necessarily think antibiotic, but the AI predicted it would be potent, and it was. Halicin works by disrupting the electrochemical gradient of bacteria. Essentially, it breaks their ability to produce energy. This is a mechanism that is incredibly hard for bacteria to develop resistance against. Halicin was the Sputnik moment for AI antibiotics. It proved the concept. But that was 5 years ago. Now in 2025, we have moved to Phase 2, the Architect. This is the era of generative AI. The problem with the Librarian approach is that it is limited by the books that already exist. If the cure for a superbug isn't sitting in a chemical library somewhere, a predictive model cannot find it. Generative AI changes the game entirely. Instead of choosing from a menu, it cooks. Models like Synthemol, developed by researchers at Stanford and McMaster University, and the newest systems from MIT, don't just screen. They design. They operate in a high-dimensional mathematical realm known as latent space. This is a complex concept, so let's visualize it. Imagine a map. On this map, every point is a possible molecule. Similar molecules are close together. The AI is told to travel to uncharted territories on this map, areas that represent high potency against bacteria and low toxicity to humans. Once it finds a promising location in this abstract mathematical space, it decodes that location into a real chemical structure. It essentially hallucinates new molecules, atom by atom, creating structures that no chemist would ever think to draw. The results of this generative approach have been staggering. The last 2 years, 2024 and 2025, have provided concrete proof that this works. Let's look at the new arsenal we have acquired. First, we have a molecule called Abaucin. This was discovered around 2023 and 2024 in a collaboration between McMaster University and MIT. It targets a specific pathogen called Acinetobacter baumannii. This bacteria is a nightmare for hospitals. It's often called Iraqibacter because it plagued soldiers returning from the Middle East. It survives on surfaces for weeks and resists almost everything. The AI identified Abaucin, and what makes it special is that it is a sniper. Most antibiotics we take are broad spectrum. They function like a nuclear bomb, killing the bad bacteria, but also wiping out your good gut bacteria, which can wreak havoc on your health. Abaucin is narrow spectrum. It targets only Acinetobacter baumannii. It jams a specific protein transport system that the bacteria need to build their outer shell. Because it doesn't attack other bacteria, it puts less evolutionary pressure on the rest of your microbiome to develop resistance. It is a precision weapon. However, there is a problem with AI dreaming up molecules. Sometimes, the computer dreams up things that are impossible to build. It's like an architect designing a floating house with no supports. Beautiful, but unbuildable in the real world. This brings us to our second breakthrough, SynthMol. Researchers realized that they needed to constrain the AI. They created a generative model that was only allowed to build molecules using building blocks and chemical reactions that actually exist. It was a recipe book that followed the laws of physics and supply chains. The result? SynthMol generated recipes for 6 novel antibiotics effective against resistant strains of Acinetobacter baumannii. And crucially, because the AI provided the synthesis pathway, the recipe, alongside the molecule, chemists could actually make them cheaply and quickly. And that brings us to the most recent news. From late 2025, MIT researchers published data in the journal Cell detailing the creation of 2 entirely new antibiotic candidates, NG1 and DN1. NG1 targets Neisseria gonorrhoeae, a sexually transmitted superbug that was on the verge of becoming untreatable. NG1 attacks the bacterium's ability to build its outer membrane, causing it to essentially dissolve. DN1 targets gram-positive bacteria like MRSA. In tests, it proved as effective as fusidic acid, a last resort drug, but it is structurally distinct from anything currently on the shelf. These molecules were not found in a library. They were hallucinated by a graph neural network that explored millions of theoretical chemical connections to find the perfect key for the bacterial lock. Now, you might be wondering, how do we trust this? One of the most unsettling things about deep learning is the black box problem. The AI spits out a molecule and says, "This will work." A chemist asks, "Why?" And the AI effectively says, "Trust me." For a long time, we didn't know what features the AI was looking at. Was it the number of carbon rings? A specific nitrogen atom? But new techniques in explainable AI, or XAI, are shedding light on this. Researchers can now generate what are called attribution maps. Picture a molecule on a screen. If the AI predicts it will be toxic, it highlights the specific atoms responsible for that toxicity in red. If it predicts antibacterial activity, it highlights the warhead atoms in green. This has revealed something fascinating. The AI is not just memorizing old tricks. It is identifying novel structural motifs, arrangements of atoms that human chemists had dismissed or never considered. It is essentially teaching us chemistry we didn't know existed. We also cannot discuss this topic without mentioning AlphaFold. While the models I just mentioned look at the chemical structure of the drug, AlphaFold looks at the target. Bacteria have protein locks that we want to jam with our drug keys. AlphaFold predicts the 3D shape of these protein locks with near experimental accuracy. The future of this field is the combination of these technologies. You use AlphaFold to build a 3D model of a vital bacterial protein, and then you use generative AI to design a drug molecule that fits into that 3D protein like a puzzle piece. This structure-based design allows for extreme precision, minimizing side effects by ensuring the drug only sticks where it is supposed to. However, despite this excitement, we are not at the finish line yet. There are significant hurdles. The first is the sim-to-real gap. An AI prediction is just a prediction. A molecule might look perfect in the simulation but fail in the real world due to solubility issues. Or maybe the human body breaks it down too fast. We still need wet lab validation, which is slow and expensive. The second challenge is data scarcity. AI needs massive amounts of data to learn. We have millions of chemical structures, but we have very little data on which molecules failed to kill bacteria. Scientists rarely publish their failures, but negative data is just as important as positive data for training an AI. And finally, the biggest threat is the economic trap. Developing a new drug costs over $1 billion. But antibiotics are cheap, taken for only a week, and held in reserve to prevent resistance. There is no profit model for big pharma to invest in them. AI lowers the cost of discovery, but the cost of clinical trials remains astronomical. Without government incentives or nonprofit funding, these AI miracles might sit on a hard drive forever. As we close out 2025, the mood in the scientific community is cautiously ecstatic. We have moved from a place of desperation, scraping dirt for new cures, to a place of abundance, where algorithms can generate millions of potential candidates overnight. AI has not just provided us with new drugs, it has provided us with a new way of thinking. It has expanded the chemical universe, taking us to galaxies of molecular structure that evolution never explored. The war against superbugs is far from over. Bacteria will eventually learn to resist even our AI-designed drugs. That is the nature of life. But for the first time in 40 years, we are no longer bringing a knife to a gunfight. We are building a machine that can evolve our weapons faster than nature can evolve our enemies. And in that speed lies our survival. Thanks for listening to Fun Facts Online.